clearance, the place where forms happen. For a number of you, that will put an image in your head. For others, you're going to learn what that image would be if you were able to make the transition. Feed clearance, what is it? Where is it measured? And what's its role in production planning? That's what we'll be discussing today. But first, why this topic? One of the most common questions I'm asked is, can I make this form in my machine? Will it fit? And to understand if it'll fit, we have to understand what feed clearance is. These feed clearances range anywhere from under 1/2 inch to 3 inches. So different machines are going to have much greater abilities than others. But to make the, to answer the question, we need to know what this is. Understanding feed clearance is also going to give you an ability to make decisions that affect your quotes and how fast you can do a quote. If you don't have to contact someone at Wilson Tool, for a question like this, it's just going to improve your quote turnaround time. So feed clearance, what is it? It's the machine's allowable workspace. So it's the area in which your sheet and the forms are created and travel about. Where is it measured? Well, it's not measured between the upper and lower turrets. That's a common misunderstanding. Right now you should see some red lines flashing about. It's really not there, because on this next slide, we'll see how a piercing die sits above the lower turret. So the distance we're talking about is from the top of a piercing die to the upper turret. This particular machine feed clearance is 787 or 20 millimeters. If you notice in the right-hand slide or image, the stripper plate is slightly recessed into the machine. And that's why we don't measure to the upper tool, just the lower tool. So what's its role in production planning? It's used to check whether or not you can make the form of the punch, right? We're answering that question, will this fit? So a feed clearance, it must accommodate the safety factor. We have that workspace, but we can never use all the workspace up, otherwise our sheet's going to run into a machine. Something bad can happen. We have to accommodate that form itself, sheet stock, and the taller die. When we're doing forms, we have to have taller dies, we call that add-on, that sit above the piercing die in order to make the form. Sometimes we have strippers that hang down because they're extra thick and they have to have relief for forms, side to side, center to center type information. So sometimes we have to account for that stripper as well. Some people might be wondering why or do we have to accommodate ejectors. So in this picture, I'm showing how the upper ejector hangs down below the turret. Now, yes, it hangs below the turret, but kind of as a practical standpoint, we can ignore that because the form can usually be removed from beneath the ejector by sliding in one particular direction or another. So to get the most out of your machine, sometimes you just have to program around some of the problems. Why is safety factor distance? As I alluded to, if we used up all the space, the sheet can hit the turret, bad things can happen. But sometimes the sheet just kind of bends. In this picture, you see how the sheet is kind of cocked, extremely exaggerated because it's a forming tool. So we have to account for that, give it a little extra safety space. And then there's just the overall sheet distortion. So we got to accommodate those sorts of things. The suggested safety distance or safety factor that I'm suggesting you use, because we are going to do a little math, is 0.12 inches or 3 millimeters. As you get more comfortable with your product and being comfortable as you're making these calculations and you're finding you're very successful and you're comfortable with your calculations being pretty accurate, you could cut that safety factor down to probably about 60 thou as a bare minimum. Now, there are some special functions, machine functions, that overcome this problem with the sheet tilting. And these are called, in a fin power, they're going to call it a retractable die station. And a trunk machine, they're going to call it an active die station. Or in an amata machine, they're going to call it the forming station or punch and forming station. And there's many other manufacturers, and they all have similar functions. So we're going to take a little sidebar, if you will, to show you the value in these forming stations or retractable systems. The whole concept is to keep the sheet flat, so it doesn't tilt up when you're using a forming tool. So in this image, we're seeing how the sheet is positioned above a forming tool, and it happens to be at the same location as a standard piercing die. So the machine's going to bring the upper punch down. The sheet didn't move anywhere. Next, the lower forming cylinder is going to move up. So it's going to travel the forming die upward into the punch. But notice how the sheet's not moving. It's not going anywhere. And then everything retracts. So you did all your forming with a flat level sheet. Trump's active die system is very similar, where they're going to want to bring the punch down, engage the sheet, and then they're going to lift that die system up, activating all the action in it, and then they're going to retract everything. The sheet staying flat. And the last one I have here is the Amata P and F. This one is different than the other two in the fact that only the internal portion of the die moves, not the whole entire die assembly. So in this case, we can bring our punch down, securely holding the sheet, and we can hold it with as much as 30 tons of pressure, where the other ones are just holding it with whatever spring pressure we allowed in the die assembly. When the upward cylinder moves, we make our form, and then everything retracts. The sheet stays level in this case. And I just encourage everybody, if you have these systems, you should investigate using them. You won't regret it, and the quality enhancement, the better quality your product is something you can sell. We have customers who make nothing more than electrical knockouts, and with the Amata P&F system, they just make them better than everybody else. The quality is greatly enhanced. So back to our topic, what's the role of feed clearance in the production planning? Well, feed clearance, it needs to accommodate everything, right? We said the safety factor, form, sheet stock, taller die, and the extra thick stripper. So the taller die, that die add-on, let's just make sure everybody knows what I'm talking about. So this picture shows you a forming tool on the left and a piercing tool on the right. And the add-on, how much taller that forming tool has to be to create a form. So now, how do you know what die add-on it is? Most forms fall into 3 tool designs or categories, and that's directly related to the add-on. There's no standard verbiage or names for these types of forms, so I'm going to call them positive forms, pass-through forms, or wipe-up 90 forms. Here I'm showing you a positive form. The die add-on equals the form height. It's a bridge, or it could be an emboss, where that die add-on and the form are identical. So it's going to simplify our math problem, if you will. So the minimum feed clearance of a positive form is a safety factor plus 2 times our form height plus a material thickness. And you can see that with the graphic identifying why, an add-on equals a form height. So that's why we see 2 of them plus a material thickness. That's all we have to accommodate. Other positive forms, or the group of positive forms, are bridges, embosses, EKOs, electrical knockouts, dimples, half shears, Lanson forms where they're that up and over. Louvers, that's most. Rare cases we can shorten it, but for the most part, you can count on a louver being a positive form. Ribs, thread forms, wheel tools, those are all positive forms. Now, a pass-through form or pass-by is where the die add-on is going to be more than the form height, because in this case, it's showing you an extrusion, and I have to shove the tool completely through the extrusion. But using some rule of thumb, some common sense measures, we can identify that the radius on a tool should be approximately a material thickness. Sometimes a little bit more, sometimes a little bit less. But it's safe to say one material is going to be my radius. So if I do that, my die add-on becomes my form height plus a material. And then to take that to what is our minimum feed clearance, it becomes that safety factor that we always want to use, plus 2 times the form, plus a material. So with a couple general rules of thumb and simple math, we can answer the questions. A pass-through form would also include card guides, coining tools where we have a pilot, extrusions, form onlys or countersinks, a Lanson form, up 90 with straight sides, progressive edge forms. I'm sure there's a couple that I missed. Now, a wipe up 90 is a category by itself, because as you see, the die add-on can be much less than the form height. Since I'm not cutting the sheet and forming it, all I have to do is kick the form up. Doesn't require me to pass beyond it. Wipe up 90, we have that rule of thumb again on the die rad. The material thickness is fine. So what we have to accommodate here, we see is a material thickness. We have a bend radius on our punch, a material thickness of straight. We have to have something, make sure we wipe at 90 degrees. So we're going to use a material thickness of straight and a material thickness for that rad. So all those create our die add-on. So what I didn't point out is the rule of thumb, straight is also material. So if we can relate everything to a material, it really simplifies the math formula. What's my die add-on? It's 3 times material thickness plus whatever the bend rad is on the punch. That's a variable that I can't put a rule of thumb on. So our minimum feed clearance of a wipe up 90 degrees. It's going to be our safety factor, or overall form height, plus 3 times material thickness, plus that bend radius. So just making sure we're following the bouncing ball, if you will. I'm giving you a little math test. It's not going to be graded, so there'll be no embarrassment. So my question to you is, what's the minimum feed clearance of this bridge? Now remember, it's a positive form. I have a form height of 130. My material thickness is 60. So remember, we have to account for a safety factor. And because it's a positive form, it's 2 times the form height plus a material. So to create the bridge in front of you, it requires a machine that has 0.44 feed clearance or more. And I do know machines on the market that can't accommodate this. Here's an extrusion. What's the minimum feed clearance on this extrusion? It's a pass-through form. It's 156 tall, 048 thickness. So if you remember the rule, the minimum feed clearance is safety factor plus 2 times the form plus 1 material. So here we need a minimum feed clearance of 480 thou. Now on a wipe up 90, this one was the oddity, if you will. It's 502 overall height. We have 60 thou for material thickness. We have a bend radius of 20 thou. Remember, the minimum feed clearance is safety factor plus an overall height plus 3 times the material, and the material is for the tool's bend radius, the amount of straight we want to go past of the tool to the form, and then our material thickness itself plus that bend radius. So here's a case where we can make a 502 form, which a lot of people don't think they can do in their machine. And the result, it needed a machine feed clearance of 822 thou. And there's a lot of machines out there that can do this. So now you know what the feed clearance is, you know where it's measured, you know the role in production planning. You can also calculate the estimated minimum feed clearance because that's your check and balance. Here's your simple formulas to refer to. And that's going to allow you to determine if your machine has the physical capacity to fit the form that you're trying to quote.